Hello everyone, welcome to Organolysis. So welcome to another video of the name reaction series. Now we are continuing our name reaction series, and in this video we are going to discuss the important name reaction that is called the fragmentation reaction. Now in case of fragmentation reaction, we have two important name fragmentation reaction that are basically GROB'S fragmentation, and the second one is the ESCHENMOSER fragmentation. So the first one is very much important as well as the second one also. So for this fragmentation we have to know some basic concepts that are related to the fragmentation reaction. So the basic concept of this fragmentation, now first we are going to discuss the GROB'S fragmentation and we will see some examples, and then we will move on to the second fragmentation reaction that is called the ESCHENMOSER fragmentation reaction. Okay, so let's start. So first, our basic concept of this GROB'S fragmentation is that we have a compound like this. Now this compound is basically has two important part. One is the electrofuge and another is the nucleofuge. Now this part is called this AB part. Basically this AB part is called electrofuge, and the second part, that is the X part, is basically called the nucleofuge. Now what is mean by that? That is what is the electrofuge and what is the nucleofuge? So first, the electrofuge, which basically lives without the bonding pair of electron. So this part I am written over here. So that is the electrofuge is basically which lives without bonding electron pair. And the second part, that is the nucleofuge, which is basically lives with a bonding pair of electron. Now it lives with a bonding pair electron, right? So this is the important concept about the fragmentation reaction, and these two terms are very much important, that is the electrofuge and nucleofuge. So when we are using this condition, that is the GROB'S fragmentation, now this A has a lone pair of electron. It basically pushes its electron over here, and these bonds go over here, and this will leave from the system. That's why it is called the nucleofuge. As you can see over here, it leaves from the system with its bond pair of electrons. So that is why it is called the nucleofuge and it is called the electrofuge. So when we are getting these three part from this GROB'S fragmentation, is that the first part is the electrofugal fragment, second part is the unsaturated fragment, and third part of this is your nucleofugal fragment. Right. So this three part is the basic concept about the GROB'S fragmentation. Now this fragmentation is basically a heterolytic cleavage of reactions of different kinds of molecules. So it is basically the heterolytic cleavage. Now why it is called heterolytic? Now heterolytic is basically it is not around the carbon. It may happen in case of carbon or different kinds of heteroatom. Now heteroatom is basically your boron, sometimes oxygen, nitrogen, phosphorus, sulfur, like that. So this is basically their heteroatoms. So for this case we have some side reaction. Now what are those side reaction? Now side reaction is basically if we have this type of compound, that is I am written over here in the same compound. If we have this one, it has two parts, that is electrofuge and nucleofuge, and there is a possibility of this substitution. So first case is this substitution. So this is your substitution case. That is, you can see here the X is your leaving group, and if you use any nucleophile, it will directly attack on the center D center and it will leave from the system as X minus. So this is a substitution case. Second side reaction is that the elimination. So elimination is basically if we have a hydrogen like this, if this C carbon or C bond is attached with a hydrogen, if you use any nucleophile, so it can take a proton from here, it can go over here and it will leave from the system. So this is your elimination case. Third case is that the ring closure method. So this is your ring closure. So the ring closure is basically this oxy A has a lone pair of electron, it will directly attack on D and it will leave from the system. So you are getting this X minus. So these three kinds of side reaction may happen in some cases. So first thing that we should remember that in the fragmentation is quite similar to the beta elimination. So it is quite similar to the beta elimination, right? So it is quite similar to the beta elimination. Now in case of beta elimination, we saw that when the leaving group and the alkene formation part are anti to each other. So when we are using a base, so as you can see over here, if we have this kind of substrate where the X is your leaving group, so X in some cases the X may be your leaving group. For this case, the X may be your SO2ME. As you can see, this is a quite stable group and it can leave from the system easily. So that is why this X is you are taking this X is equal to SO2ME. And if we are using any base, so that's very much important to remember that in these cases, this is your if you saw the product, then you can see there is a 1,3 difunctionalized compound. Now what is mean by 1,3 difunctionalized compound? That is, this is your 1, 2 and 3. As you can see over here, this is your 1,3 difunctionalized compound and this is conformationally locked. So you can see over here, this is a cyclohexane form. So that is why it is conformationally locked system. And in this case, if we are using any base, there is a formation of the carbon-carbon double bond and the bond breaking between this carbon X, that is CX bond. So how this reaction takes place, you can see over here, this base takes a proton from here, these bonds go over here and there is a bond formation between, as I told earlier, that is the carbon-carbon double bond formation is being takes place and it will leave from the system. So as you can see over here that we are using a conformationally locked system and we are getting a compound which is a chain or chain type compound. So what will be the product? So product should be like double bond O and this is your R group, right? So this is your major product from this compound and this is a quite important example of this fragmentation reaction. So that is why this is very much important. Now let's see the mechanism. So mechanism is very much important. So for this GROB'S fragmentation, the mechanism is quite basic and it is believed that the mechanistic pathway can be achieved by 3 ways. Now what are the ways? So if the first possibility is that if this A has a lone pair of electron, it can push its electron over here, it can go over here, as we see and earlier that this kind of 3 fragments we are getting. So this process is basically called one step synchronous, right? So this is first method to identify the GROB'S fragmentation. Now the second process is that if the X will leave from the system, so if the X is quite stable group, so it can leave from the system easily, so then we are getting this kind of intermediate and this lone pair push back over here and it will get over here. Now we are getting the same product from here. So this is our major product from this kind of reaction. So this is basically called the 2-step cationic pathway. So this is basically the 2-step cationic pathway, right? Now the next point or the third type of mechanism is that if we have this lone pair over the A and it will go over here and it can go over here like this. So the first, that is the electrofuge part, will leave from the system. So as you can see over here, this electrofuge part will leave from the system first, then we are getting this negative charge, actually this negative charge over here, that is C in minus, and we are getting this intermediate, and so you can see over here this is the anionic pathway. So that is why this method is called 2-step anionic pathway. And then the final step is that it will push over here and it will leave from the system in this way. So we are getting this C double bond X, that is the unsaturated part, and this is the fragment part from this reaction. So as you can see, this mechanism is there is three types of mechanism, and there is an anti-periplannar position is very much important. I mentioned over here, that is the anti-periplannar position is very much important, and it is quite similar to the beta elimination reactions. So this is all about the GROB'S fragmentation, and let's see some examples that are very much important. So first example, we have this trans-decalin type system. So we can write this, and we are using this base, that is the tertiary butoxide, and we have this kind of trans-decalin system, and OTS have the as a leaving group. So we can write this system in this way. So we can write this way. So this is your trans-decalin. You have the hydrogen over here. We have the OH over here, and the tosylate group is present over here. So this is your OTS group, right? And here we have the hydrogen. Now when we are using the potassium tertiary butoxide, that is this one, so this is a base, so it can take a proton from here. So how the fragmentation takes place, let's see. So this negative charge can take a proton over here, and it can go over here, and this bond go here, and this OTS will leave from the system. So the important concept of this reaction is that the type of alkene formation is either this alkene is cis or the trans. So you can see over here, these bonds go like this, and these bonds go like this. So when the double bond formation over here, so these two are trans to each other. So that is why when we have to write not in this chair form, we have to write in normal way. So we have to keep in your mind that the alkene formation which is formed during this fragmentation, it's trans. So when we are writing in this way, that is this one, and this is your double bond, and the double bond position is this. So because of this, so you can see over here, this is a trans alkene. So if you can't get the point, if you don't get the point, so you have to numbering from here. This is your 1, 2, 3 and 4, 5 and 6. So you can see over here 1, 2, 3, 4. This is your 5, 6, where the alkene formation is being takes place. So you can easily remember by using this numbering condition, or you can easily remember that the alkene formation which is trans to each other. So you have to write this product, and you have this question, I guess question came in CSIR-NET previously. I didn't remember the exact year. So this question is very much important. The similar type of question comes that if we have the cis-decalin, then what will be the product and how this reaction takes place. So let's see. So you can see over here, this junction is cis to each other. So you have to write this decalin, this chair form in this decalin in a chair system. So, and it has to be the cis one. So for that, we have to write this one first and this one. So this is your cis-decalin. Now you have to mention the hydrogen and OH. This is your hydrogen, this is your OH, and we have the OTS like this. So now when we are using the base, the similar base, we are using the potassium tertiary butoxide. So this base takes a proton, it will go over here, and it will go here, and it will leave from the system in this way. Now see the alkene formation, how either this alkene formation is cis or trans. So you can see over here, that is this bond, and this bond if the alkene formation is being takes place, and these two are in the same side, these bonds and this bond are in the same side. So that is why we can easily predict that this is alkene formation is being takes place in this case. So our product should be like this. Now see, the important concept of this reaction is that you have to use this double bond O in this position, so that you can easily write the double bond in the cis way. So this, in this position you are getting the alkene, and you can see over here, this is the cis alkene. So that is why this reaction is very much important. And how can you identify? You can easily identify by numbering. That is, you can, if you write over here, this is your 1, this is your 2, 3, 4, 5 and 6 position, this is your 7. So you can easily predict, that is, this is your 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 and 7. So we are getting the alkene over here in this position, right? So this is how we can get easily that this is our cis alkene or not. Okay, so let's see, let's move on to the next example of this reaction. Is that if we have this kind of substrate and we are using the sodium hydride, so we know what will be the product, and you have the leaving group is there, that is the OMS, that is your methyl group. So it's also acts as a leaving group. So that is why when we are using the sodium hydride, that is H minus, so it takes a proton from here. So these bonds go over here, it will go over here and it will leave from the system. So this is similar kinds of mechanism is being followed over the all the cases, and we are getting this kind of product. Double bond. Here we have double bond, this is your OM group and double bond like this, right? So we are getting this kind of product. Now let's see the another example of this reaction is that this one. Now this question I already made a video on this question, that is basically solution of choice based question. You can go over here to check out that video. I have explained detailed that how this reaction, overall reaction takes place. Now this question is quite important just because of this question has the 2 times GROB'S fragmentation. So see first how the 2 times GROB'S fragmentation is being takes place. So when we are using the sodium hydride, we know that with this OH bond like this, so this H minus takes a proton over here, it can go over here, these bonds go here and it will leave from the system. So this is the first time we are getting the first fragmentation reaction, that is this one, and the product we are getting is this. This is your double bond, C double bond O. Here you have the OH and this groups like similar in this way. That is this one. So we are getting this kind of product. Now the second important point is that when we are using the methyl lithium, so you know this is a heart center and this is also your heart center. So this methyl directly attack over here. So we are getting this this methyl lithium. So it will attack over here. It will go like this. And after this hydrolysis and the workup, we are getting that product. So I am not written the overall part because I have already discussed this question. So that is why I am not written over the whole concept, right? Now why this reaction and the stereochemistry of this is very much important. That is, this is your OH, and why this methyl is in below and why this OH is up, and you can watch that video. I already discussed that point over the video. Now the second point is that when you are using the tosyl chloride, now we have this OH, it directly pyridine takes a proton from here and we are getting this OTS group. And the third point is that when we are using sodium hydride, now this is the case that when the second time the GROB'S fragmentation is being takes place, that is this H minus takes a proton, it will go over here and this go over here and it will leave from the system. So finally we are getting a big compound, a large ring type of compound, that is this one. Methyl, this one, right? So this is all about the product from this section. So see, the 2 times GROB'S fragmentation is being takes place. This is the first one and this is the second time, right? So let's see another examples. See, when we have this kind of substrate, this is the OMS, so this is a leaving group over here, and we are using this B2H6 NaOH. Now what will be the product? Now you don't think about the fragmentation and reaction, but in this case the fragmentation is being takes place, and how this fragmentation takes place I will show you here. Now you know that is a hydroboration reaction. So when we are using B2H6, so it will attach with this double bond. So for that we are getting this kind of intermediate like this. Okay, so this is the position that we have the alkene, and this is your methyl, and here, and this is your OMS like this. Now this is in this position the alkene is being takes place. So after the hydroboration we are getting that is this one, and along with this is the hydrogen, and here you have the 2-methyl. So these are the 2-methyl. Now when we are using the base, so that is how this fragmentation is being takes place. See the mechanism. This OH is directly attack over the boron center. It will go over here, and it will go here, and this OMS will leave from the system. So that is why how this fragmentation is being takes place. So this is a very good question, and the question may come in this from this type of question, right? So see firstly how the alkene is being there, that is either it is cis or trans. So you can see over here that is the trans alkene is being takes place. So we have the trans alkene in this position, and we have the 2-methyl, and in this position we have the alkene which is also in trans, that is because these two are trans to each other. So similarly we get the alkene over here. Now next question is that this question is basically the Asa-Grob fragmentation. Now this 6th question is basically the Asa-Grob fragmentation, how this reaction takes place. See, now when we are using sodium borohydride, this H minus directly attack over here, and it will go like this. So we are getting this O minus and H. This is how. Okay, now these bonds can go here, and it will go here, it will go like this. So that is how we get this type of fragmentation reaction by using only the sodium borohydride. So this is how that is why this reaction is called the Asa-Grob fragmentation. This is the double bond CH2 CH2 OH, and here you have the nitrogen, and this double bond CH2 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 3CH2, and this S minus, right? And finally we have the sodium borohydride in the reaction medium. So this aldehyde also reduced, and this imine also reduced in this way, and this hydride also reduced to the primary alcohol. So we are getting the final product, this one, and that is what it is, and it is finally protonated, and we are getting this SH. Okay, so this is the overall product from this reaction. Now let's see, and we are going to discuss the Eschenmoser fragmentation, how this reaction takes place. I already made a video on the Eschenmoser fragmentation reaction, so that is why I am not written over here the overall concept of all this. So you can go over here to check out that video. So let's see some Eschenmoser fragmentation. So first we are using the H2O2, then we are using this tosyl hydrogen or this type of group, and finally we are using the base. Now we are from this type of 2 6-member ring, we are getting this kind of large ring, that is we have along with this triple bond. Now let's see first that when we are using H2O2 NaOH in this alpha beta unsaturated compound, we know what will be the product. This in this position the epoxidation is being takes place. So the epoxidation is being takes place over here by after using this H2O2 NaOH, right? So I am not written over here how this NH2 to NaOH attack and how the epoxidation is being takes place. So see the next part is that we are using this group. So you can see over here the tosyl group. So we are using the tosyl hydrogen. So it is basically TSNH2, and how this one is being formed. See, so we have this type of group NH/TS like this. Okay, so now when we are using base, so this in hydrogen is being protonated, so we are getting this N minus, so we are using the base. And how you are getting from this one to that one, that is hydrazone, how we can get, I already made a video on that topic, so you can go over here and check that video also, how this reaction takes place. That is why I am not written over here. So now this O minus takes a proton from here, it can go over here like this, it will go over here, and it will go like this way. Similarly, from we have this O minus, right now we have the double bond, that is N, double bond N, TS, like this. Now the second step of this reaction is that this O minus go over here, it can go over here, go like this, and this TS will leave from the system. As we know that tosyl group is quite important leaving group, so from that concept we are getting this large ring. So you can see over here the triple bond is being formation over here, and finally you are getting this product. Let's see some examples for this question. We have this one, when we are using H2NOH, so this will be our product, that is epoxidation first, and then this one, and the final tosyl hydrogen is given. So this is quite similar to that mechanism, and that is the Eschenmoser fragmentation. So when we are using TSNH NH2, we are getting that one in NHTS, and along with this whole group, and finally the product we are getting from here, that is after this from after this leaving group leave of this from whole group, we are getting this one CH, and along with this like this. Okay, so this is all about the product from this question. Now let's see another example of this Eschenmoser fragmentation is this one. Now when we have this one, so I have not written over here the overall reaction mechanism, so I already made that video, and this this question is I think this question was came in CSIR-NET, so that's why I am not doing this whole mechanism. I already written over here the final product only. As you can see, this is your final product from this one to that one. So this is all about the GROB'S fragmentation as well as the Eschenmoser fragmentation, and I think I have covered all the topic, all the examples, and what are the probable questions. These two are very much important, so these two may come in upcoming examinations. So I hope this video is very much helpful for you, and keep sharing my videos in your friend circle. And if you like this video, do not forget to subscribe and press the bell icon to get the earlier notification, right? So that's it for this video, and thank you so much for watching.